You can start.
Yes, sir. Yes, welcome, madam. Good afternoon, webinar on sensors and applications. Really, it is God's grace that we are safe with pandemic situation all over the world. God has protected us and has given us a chance to gather as one family under this meet. Let us invoke God's blessings through the song, God Will Make a Way.
Ma'am, not hear your voice, ma'am.
Couldn't hear my voice, sir.
Yes, ma'am.
Hello. Sir? Hello? Hello?
Ma'am, you're audible, ma'am.
Yes, yes.
You can play the song, ma'am.
Yes, let us invoke God's blessings through the song, God Will Make a Way.
God will make a way where there seems to be no way. He works in ways we cannot see. He will make a way for me. He will be my guide, hold me closely to his side. With love and strength for each new day, he will make a way. He will make a way. Oh, God will make a way where there seems to be no way. He works in ways we cannot see. He will make a way for me. He will be my guide, hold me closely to his side. With love and strength for each new day, he will make a way. He will make a way.
This webinar being on sensor, I would like to say a few words about sensors and applications. A sensor measures the physical input and converts it into data. Most of the sensors are electronic. A simple sensor is a glass thermometer which observes the heat and shows the temperature. The important characteristics of sensors are sensitivity, resolution, linearity, drift, range, repeatability, and reproducibility. There are different types of sensors and they find a variety of applications in industries as well as in our day-to-day life. Sensors are used to make lights on and off automatically at a particular time when the people are out of station. Gas sensors and humidity sensors are used in cell phones. Light sensor is used for the automatic brightness adjustment of the cell phone screen. In Android smartphones, to locate the device place, geomagnetic field sensor along with accelerometer sensor is used. Position sensors are used in ATM machines. Airbags used in vehicles for protection during accidents works only on the principle of sensors. Alcohol sensors are used to detect the alcohol intake of drivers. This webinar is focused on sensors due to its importance and variety of applications. Eminent persons working on this area will share their knowledge during the 3 sessions of the webinar. For today's session, we have in our midst an expert scientist from Germany, Dr. SriRanjini Arumugam from Leipzig University, Leipzig, Germany. Dr. SriRanjini Arumugam is an experienced scientist working in the field of biophysical chemistry with a practical knowledge in developing new applications and products. She is a recipient of research grants and she is highly skilled in overseeing research office activities. She has got many applications in internationally reputed journals. She is a mentor to UG, PG, and research students and also a public science communicator. I am proud to say that Dr. SriRanjini Arumugam did her college education only in Tamilnadu, India. Completed UG chemistry from Holy Cross College, Trichy, and PG chemistry from American College, Madurai. She received her PhD degree from the prestigious institution, Indian Institute of Science, Bangalore. She did her postdoctoral fellowship in Pennsylvania State University, USA on DNA replication and repair using bulk and single molecule spectroscopic methods. After completing her postdoctoral fellowship, she worked as research scientist for 7 years from 2013 to 2020 in Max Planck Institute for Biophysical Chemistry, Göttingen, Germany, exploring the spectral properties of diamonds for biological systems using imaging and sensing. Currently, Dr. SriRanjini Arumugam is offering her service to Leipzig University, Leipzig, Germany, as a senior scientist concentrating on her research work on diamonds. She is a simple and approachable person. I appreciate her readiness to share her experience and knowledge in this international webinar on sensors and applications. We are privileged to have such an eminent person in our midst on this day. On behalf of the management, faculty members of Department of Physics, Auxilium College, and the participants of this webinar, I extend a warm welcome to you, Madam. Hearty welcome. I also extend our warm welcome to the participants, PG students, final year BE students, research scholars, faculty members, and eminent persons from various institutions of India and abroad. I am sure this webinar will provide a platform to gain and share knowledge with scientists. Welcome one and all. Thank you. Now I hand over the session to the resource person, Dr. SriRanjini Arumugam from Germany. And I also want to tell, after this presentation, we will have the question session. The participants attending through Zoom Meet can unmute and you can put your questions directly to Dr. SriRanjini Arumugam. Now over to Dr. SriRanjini Arumugam.
Thank you very much, ma'am, for your kind words, and very good afternoon to everyone. And this is I am from the Leipzig University here, as ma'am said. And let me share my okay. So let's get started with our focus. So today I will brief you about some of the uses and applications of special type of diamond, which is called NV centered diamond, which is nitrogen vacancy centered diamond, as a sensor material. So I outlined my talk like to give you a little introduction to sensor, which ma'am has already given you a very good introduction and different sensor types and example. And I'll brief you on how a NV diamond can be used as a sensor and its applications, where I have quoted some publications from our group and our collaborator groups. And finally, I would like to conclude my talk. So what you see here is a pretty picture of what we call it as a sensor world. So it is basically Internet of Things, which bridges the gaps between the physical world and the digital world. So in today's everything is, most of the things are digitized. Um, and what's behind the digital world is basically a lot of sensors. So this is what we call it as the Internet of Things. So this, all the sparkling spots are connected with the digital, which connects the digital to the physical world. So sensor is nothing but they are the heart of any innovation. So always it is the technology which drives the sensor innovation for more towards advanced computing and find the solutions. And we always talk about analog, and nowadays there are a lot of smart sensors. So analog is a kind of or a standalone sensor is something which has its own value. But when the sensor is smart and connected, it can be it can create a value that exceeds its intrinsic value. So to define a sensor, so it is nothing but a device basically which responds to changes in a physical phenomena or environmental variable, like as ma'am mentioned, like heat, pressure, humidity, movement, anything. So this change in this physical or chemical or electromagnetic properties of this material is processed to more usable and readable form. They are nothing but they are heart of any measurement system. They are the one first, they any changes happening in the environment or whatever we want to study, they come into contact with that particular variable and generate an output which we term is a signal. So they can be interpreted as such as a readable form, or can be connected to the different type of sensors and other instruments, or various type of things in which you can call it as a smart sensors. Different type of sensor. It is basically what ma'am said. It is based on the quantity that's being measured. So one of the best example is the temperature sensor, both digital and analog. A thermometer is a good sensor, and which can we can use for distance measurement, and IR sensor, and so on and so forth. One good example is very popular among particularly youngsters is the wearable sensors, which is mainly for healthcare, improving healthcare and health outcomes, and for improved health management and betterment of life. So in this, we see in watches, we see like Fitbit, we have so many gadgets which is in the wearable sensor format. So if you take the flexible and wearable physical sensing platforms, they're made up of sensor materials, like a flexible template materials. Sensing element either can be solid state or liquid state, or they can be, they work by mechanisms like pressing, stretching, bending, or twisting. And they're not only like Fitbit or a smartwatch, we have various applications in which artificial electronic skin, therapeutic drug delivery platform, and a lot of the physiological applications. So this is one example of an application of a sensor to do in day-to-day life. Other than it's in a broad area, you can be having from automotive industry, medical, lot of sensor, industrial, aerospace, motorsport, and agriculture. This is like some gross broad area of applications of sensors. So what are the materials that is being used to make these type of sensors? Ma'am has already mentioned about the properties which mean, or the qualities which makes a sensor, a material to be make a sensor. So here the material science and engineering of a sensor material is a very vast and a thriving area. So it is micro and nanotechnology advancement which makes this field always a progressing one. For examples, materials which can be used as ceramics, polymers, hybrid materials, piezoelectric material, and wide range of nanomaterials. So out of which today I will talk on diamonds. As we all know, diamond is an allotrope of carbon. So basically it's made up of network of carbon atom connected to one another. When they connect in a different way, you get three different materials. When they connected in this kind of fashion, in this geometry, this diamond, when they are in a linear and they get it, what we get is graphite. and when they are connected completely like a ball, they are the buckyball or the Buckminster Fullerene. So when we have a perfect diamond which is transparent in nature, but there exists also colored diamond in nature. So this we call it as color wheel of diamonds. So you can see a pretty beautiful colors of various diamond and shapes. So we all know diamonds are used in mostly in jewelry, and it is got from mining from various mines of various countries. So as we get the naturally occurring diamonds, 1 in 10,000 diamonds has a color which is other than white, and it has its own reason. For example, if you have a blue one, it has a lot of, other than carbon, it also has a boron rich in diamonds. And yellow has nitrogen rich. Likewise, not only the other element other than carbon is present makes them colorful, there may be some defects, like the way it is when the structure is arranged. Sometimes there may be some defects, some extra impurities or extra material present which makes them colored. So what is nitrogen vacancy center in a diamond? So what you see here is a unit cell of a nitrogen vacancy center in diamond. So as I told you before, it's all made up of carbon, that is black in color. All the carbons are marked in black. So you take out one of the carbons, you knock out one of the carbons and replace with nitrogen. So you get a nitrogen center in diamond. And also knock out the adjacent carbon and make it as a carbon vacant site, and it is balanced by the lone pair of electron from the nitrogen. So the valency is satisfied and it's very stable system. So such defect or such diamonds which are made with such a process are called nitrogen vacancy center in diamond. So these vacancy centers act as actually the sensor or the probe for whatever studies we want to do. They can be manipulated both by light and microwave medium. And when you shine them with a light, they emit colored photons. Basically, the colored photons will carries the quantum information about the surrounding magnetic and the electric fields. So advantage of this is it acts as a dual sensor, in the sense it acts as a both magnetic sensor as well as an optical sensor. So this property can be used for various applications like bioimaging, neuroimaging, object detection, and various other applications. I will come to some of the applications a little later. So how do we produce such a diamond? We can also use a naturally occurring mine diamond, which is more expensive. So we do make it in the laboratory scale or industrial scale. So where we do the production of single crystalline diamond. So it is high pressure, high temperature method in which the industrial production is done. You can see this is one typical setup. And diamond we get here is little impure because of the industrial scale, the production method. But if you do it in a chemical vapor deposition in laboratory scale, we can get a very ultra pure material, which is ultra pure diamonds substrates. So once we have the ultra pure diamond substrate, then the next stage is to make the NV defects. How do we do it? We take it in the plasma chamber and take this is the diamond lattice, and we impinge with nitrogen gas ions with ionized nitrogen, and then we try to knock out one of the nitrogens. So in this way, and then if you image that, if it is then we can find all the bright spots are where the carbon is replaced with a nitrogen. So these are the image. This is the image or the signature of the nitrogen containing diamonds. So how do we make the nitrogen? I showed you how do we make the nitrogen diamonds, and now I'll explain you about how we make the nitrogen vacant rich diamonds. So we take such a nitrogen diamond and then irradiate like 35 electron volt, and then irradiation basically it collapses the structure a little bit. And then when we anneal at 800 degrees, we have to slowly anneal it. In that case, when the structure is reformed, what happens is the nitrogen is retained and the next section is the carbon is knocked out and a vacant site is formed. And these can be characterized by doing a very good TEM or the wide field confocal imaging or confocal imaging. So basically you take the diamond and create the vacancies and migration of vacancies at 800 degrees when it is cooled, and followed by when you put it in a milling ball milling machine and you get it. This is the kind of this is a very very small nano sized diamond, less than 10 nanometer in size. So they are kind of blackish shoot. It's like a blackish color suspended in ultra pure water. So, as I mentioned before, it does act as a both optical sensor as well as a magnetic sensor. So, this as an optical sensor, this act like a single photon source as a fluorescent marker, biomarker. For studying, it's like a fluorescent biomarkers, and it has very low, very high photostability and low cytotoxicity. So it is very good for very best for studying the biological system. And also, it is helpful in detect and measure the number of physical quantities like magnetic and electric fields. And this is very much used in super resolution imaging. And the spins for the by using as the optical readout, we can actually detect the spins of the system, spins with other any system of interest, and this can be used for quantum information processing and quantum meteorology. How it is act as a magnetic field sensor. So here is a diagram to say relatively comparing with respect to the Earth's magnetic field, and then various sensor which you must be familiar with: Hall, GMR, and Squid. And these are the various. This is the scale in which they are sensitive. So when we compare various sensors, we have to also consider different parameters, something like sensitivity, linearity, range, bandwidth, dimension, etc. So if you take into these different things, our NV sensor falls in this red, which is marked in red, and then which is pretty much from about micro Tesla to almost like sub nano Teslas. And not only this, you all know Squid, Hall, GMR all needs high superconductors, and then they need a super cool temperature with helium or other noble gases. But NV sensor act is it's very simple, and you can use it as a room temperature. That's the biggest advantage of having a sensor which can be operatable at a convenient room temperatures. So this makes the design of the instrumentation very simple. So considering the applications, so some of the applications are in the solid state spintronics, quantum devices, subcellular micromolar cellular imaging, biosensors and technology, and protein structure analysis. This is some of the, I have given some broad applications. So going into some of these some of the spectroscopic properties, which is like a signature for this nitrogen vacancy center, one of them is the optically detected magnetic resonance. You all must be knowing about magnetic resonance. Here, what we do is we do magnetic resonance by using optics. So this is the ODMR, optically detected magnetic resonance. So considering the simple Jablonski diagram of the NV center, so here we have this, it is a triplet state, A triplet to E triplet transition, ground state to the first excited state. And when you impinge, when we pass, when we hit with a green laser at 532 nanometer, it goes to the E3, the triplet E3 state, and then from the spin state m is equal to 0 to m is equal to 0 of the ground state, it comes back with emitting a red light at 628 nanometers. So this is 100%, and we call it this a bright state. But also it transition to another intermediate singlet state, triplet A, and then also to from the other spin state ms equal to plus or minus 1, and comes back, and then there is some of the radiation lost in that pathway. So this is called as a dark state. So we have a two distinct, one bright and the dark state. So by applying microwave, we can actually manipulate, we can actually study the spins states, the difference in the spin state between the dark state and the bright state by applying a microwave across. So here is what is put it in a graph, what I explained you here. So basically we are looking into the fluorescent counts of the red. So as for this, whatever is like goes like a baseline is a bright state. So when there is a difference between the bright and the dark state, there's a dip at 2.84 gigahertz. And then this is with no external applied field. And when it goes back to the resonance, goes back to the full emission, then it goes back to the baseline. So this is a very signature of the NV center diamonds. So what we do with this, we can sense DC magnetic fields. So here it's a very classical example of looking into a single Zeeman effect splitting in the single spin. So this is what I showed you earlier with applying microwave frequency. We can actually look into this difference between the bright and the dark state. But when we start applying an external magnetic field like 3 millitesla, 6 millitesla, 9 millitesla, you can see the splitting, the Zeeman splitting goes as the strength of the magnetic field is increased. So they can be used as a far field probe or atomic vector magnetometer, and they are absolute and there is no calibration needed, and the sensitivity depends on the line width. So they are improved by using coherent manipulations. So in nutshell, to put it, so they can be used as to sense any DC magnetic field, the systems with any DC magnetic field is generated. So they are typically nano-size sensor, less than 10 nanometer, and it is atomic because it is just a nitrogen and a vacant site, and long coherence time, more than 2 millisecond, and very high magnetic sensitivity from microtesla to nanotesla. So how do we image this such NV defects? So this is the schematic diagram of the how the experimental setup in our lab is. So this is a closer view at the microscope, microscope objective. So this is the objective, and this is where we have the diamond incorporated in NV center diamond incorporated into it. So we apply a green light which passes through this, and which emits a red light which can be collected through this geometry, and on the plane, on a horizontal plane, we apply a microwave to manipulate the fluorescence reading, and then across a coil is also kept in order to apply external magnetic field whenever necessary for the experiment. So this is another the schematics in which you can see this is the study which is study of interest. And then you have this NV center kept, you can do both ways. You can have the diamond on the surface and put the molecule on it, or molecule and then place the diamond on it. I'll come to that later. So this is a typical NV centers. And if you zoom one of the point, this is how the NV center bright fluorescent spot is. Each spot you can see under the microscope. So what we can use, one of the uses is to build a precision NV magnetometry. So here we have this is from the picture from the lab. This is a sample and we have a laser light going through it. So in a typically, if you put it in schematics, these are the various different molecules of interest to study on the surface. Particularly, this is useful for non-transparent samples and thin films. So we have you all know about the AFM TM, and in which cantilever we have, and on the tip we attach the diamond, and as we scan, as they are different distance from the surface, they can have a different magnetic field which can be sensed. So they can be sensed very precisely up to 1 microtesla using the NV diamond in nanocrystals. So this is very important and useful in studying ultra thin magnetic films, vortices, domain walls, and molecular magnets. And another application is in which looking into building a nanoscale NMR of per proton spins. You all know, most of us, you would have seen the NMR instruments, which are very bulky and expensive and things like that. There are there have been very many experiments going on in order to achieve a room temperature and very simple tabletop type of NMR instruments. So here we have, for this doing this kind of experiment, we have normal NMR sequences will not be useful. So we define two different NMR pulse sequences, which we call it as dynamical decoupling and also dynamical sensitivity control sequences. And the pulsing sequences are basically used for filtering spin interaction and sensing the spin noise. So here we have a NV center buried about 5 nanometer from the surface, and we have a proton bath, basically ultra pure water, and apply an external magnetic field. And when we have this going on, we can actually sense the Lama frequency of the proton at 1.81 megahertz. We can very well see in the bright state, and when you do it in the other way, we can also see it. So this is with the dynamical decoupling sequence XY8. When we use the disco type of sequences, we can actually do the 3D projection on and see how the surfaces of the proton spin looks like. So this gives us very encouraging, and we are on the process of doing it for small molecules and extending to the larger molecules, looking into the proton spin. Not only proton, we can also look into the COSI type of experiment with proton with carbon-13 or nitrogen nuclei. So those kind of experiments also are ongoing. Another application is to use as a thermometer inside a cell. So we call it as a nanothermometry because these are very nanometer in size, and using the NV diamond. So the operational principle is you have it, you implant inside a cell, and then when there is a transition in frequency, which can be optically detected with high spatial resolution. So mapping the fluorescent signal, actually doing the ODMR and the mapping the fluorescent signal, one can actually interpret the temperature correlation. So in this work, it is done with a collaborator. So a single human embryonic fibroblast cell is taken, and in which this nitrogen vacancy center diamond is implied, and it is it is given, and also for control, there is also with the one with the nearest to this the gold nanoparticle, in which it transfer the electron. It is for control. So if you look into this experiment, so basically you have a incidence of green light, which is 532 nanometer laser, and when it emits the red fluorescence, and then you get with microwave radiation, and then you manipulate the potential studies using this type of methods. So here the nanoscale thermometry, this is the signature of the NV diamond, and as we change different laser power, that we can actually convert this to this using a different formula, and then looking into this, you can correlate with respect to the laser power and the temperature variation. So not only the power dependence, you can also look into the distance dependence. For instance, A to F is the how close the heating, what you want to look at from there, the spots from the center of the NV center to the various spots. So as we go from A to F, you can actually very well see how very small changes in the temperature, but you can actually see it very clearly by doing these experiments. So it is possible to detect as small as 1.8 millikelvin using this type of temperature measurement inside the cells. So why it is important? Because there is a difference between, for example, there's a difference between normal cell and a malignant or cancerous cells. So there's a temperature difference. So these all can be incorporated, in which there is a need for looking into the temperature difference within the biological systems. Other example is sensing metalloproteins. This is also another, we did it with our collaborators. So here, the advantage, you can detect single protein in a biological environment, and it has a wide range of application in the life sciences. So here we have taken the ferritin proteins, which has the name, you can, from the name you can understand that it has a iron core. So it is found in various organisms. Their primary function is the iron storage. So if you take into the ferritin concentration in blood, it's correlated with the total amount of iron stored in the body. So iron, we all know about the anemia problem we have, particularly women. So one such responsible is the concentration of the iron in the body. So this protein is critical for hemostasis and metabolism in mammals. So in this experiment, what we did is we took the nitrogen vacancy diamond as a biological sensor and then incorporated into the ferritin. So this is the high resolution TEM picture in which the ferritin is taken, and you can see the ferritin molecule and the nanodiamonds inside incorporated into it. So here we have the system of ferritin with the incorporated nanodiamond and looking into the fluorescent decay. So this is a typical picture of the T1 relaxation time of both with respect to the nanodiamonds with ferritin and the nanodiamond itself, free diamond. So here we see, if you look into this, we can actually do an histogram of a single, we are talking about single protein in this case. We can have a histogram where this is the free nanodiamonds, and average of T1 relaxation is 41.8 microsecond, where this is with which is incorporated with the protein, about 5.5. 5.7, about 8-fold difference is there. So there you can actually clearly distinguish between the one which is free, one which with the protein. So in this way, we are able to detect the individual ferritin molecule. So it is very sensitive technique, which can use to detect the single protein, and it can be applied to any cellular environment. And this is important, for instance, for studying important biological process like electron transfer mechanism. So another application in our lab, we developed not only this, so far I have talked about all the involves microscope function. So here what we do is precision sensing use tapered fiber. So as a physics background, you all must be using a lot of optical fiber for your various experiment. So here what we do is we try to take the microscope module into a different flexible, where the flexible module using optical fiber is needed. So here we used an optical fiber which is used to excite both the nitrogen vacancy center and also collect the fluorescence. So we are building a NV best flexible sensor. So we have constructed a miniaturized fiber integrated sensor modules for multiplex sensing and simultaneous signal acquisition. So this type of tapered fiber sensing mechanism is mainly useful for multiplexing, and particularly not from one spot. It is used for collecting signals from various spots simultaneously. So this is the fiber. This is a fiber in which the top, the end with a nitrogen vacancy diamond is attached. You can see that green light is the laser, and the red is the fluorescence that is emitted. This is a cross section of the picture, and this is the fluorescence of various type of signals, fluorescent signal from a various type of different type of cut. Fiber with like a time of flight type, a flat fiber end, and fiber, different types and the different thickness of the fiber. So what can we do with this? One thing we are trying with our medical school is to build a NV-based optic, NV fiber-based optic based endoscopy. So basically, will be a state-of-art endoscopy, which has a long flexible tube, which has the length and the flexible depend on the part of the body doctor wants to see, a fiber optic light, a camera lens, and another channel for any other medical instrument if necessary. So basically, the fiber optic light will be, and then in which you attach a diamond, and also you say you can send a 532 nanometer light, and then you can use for various diagnostic purposes. This is one we are trying, ambitious project we are trying with the medical school. Another ambitious project what we are trying with is to construct a nitrogen vacancy center based magnetoencephalogram, which is to image the brain. So, considering the various scanners, the imaging methods which is available in market is PET, functional MRI, MEG, some of them. So you can see their time resolution and their spatial resolution. And this is very good in time resolution. We have such a thing with NV Center, we can have both in time resolution and the spatial resolution. So it falls between the MEG and functional MRI, and it has a very good scope for in this area. So if you look at this onto the left, you can see the picture of a conventional MEG, or like even MRI machines you might have seen. So here, what you say, why it is so bulky is because it has the squid based superconductors, and the cooling, it makes them so heavy, and it is actually fixed to one place. But when you constructed something like very flexible using optical fibers, you can actually put it in various points across your skull and image various simultaneous imaging, which I called as multiplex imaging, using a fiber optic based imaging. So this is the second ambitious project, ongoing project with the medical school. So these are some of the applications what we have done also with the collaborators groups, which has a very wide field of applications. So with that, I move on to the conclusion, in which you might have understood that there is always this field is driven by a lot of technological advancement, particularly micro nano technology, novel materials, smaller, smarter, and more effective electronic system. So they all play a very crucial role in future applications, and taking this field forward. And not only the technology in this way, but also the opportunities for such emerging technologies is using the NV defects is not only limited to this. We are looking into the various application, which is for like brain computer interface, augmented prosthetics to point of care medical diagnostic devices. So looking into the prospects of the diamond-based quantum sensors, it's very promising. So they are this very evident from the various application that they are the possibility to deliver new tools and technologies, and which can surpass the current technologies. Basically, what we are trying to do is to benefit the humankind and beyond. With that, I move on to the acknowledgement. So most of this work is done in collaboration, and I'm a part of the group with Professor Gopalakrishnan Balasubramanian and his group at Leibniz Institute of Surface Engineering in Leipzig, Germany. Also the Leipzig University where I work in Leipzig, Germany. And most our group moved here last year during the pandemic time. So we are in the process of setting up everything here. And most of the published work has been done in the Max Planck Institute of Biophysical Chemistry, Göttingen, Germany. And the money comes from Max Planck Group, Volkswagen, and ERC and DFG. With that, I thank you all for your kind attention, and I'm ready to take questions. Thank you.
Yes, thank you, madam, for your valuable presentation. Thank you very much. Now we will have the questioning session. I request the participants to unmute and put forth your questions. One by one, you can unmute.
Ma'am,
Yeah.
ma'am, sensor
yes.
means what, ma'am?
A sensor is nothing but a material which can be used, made to make a device, which is going to respond to the changes in the environment in the form of electrical or magnetic, or it can also convert one form of energy to another form of energy. So this is something which can sense the change.
Ma'am,
Yeah.
ultrasonic sensor means what, ma'am?
What's, pardon me?
Ultrasonic sensor.
Ultrasonic sensors are sensors which can detect the ultrasonic rays.
Yes. Moisture sensor means
Which can sense the changes in the moisture in the atmosphere.
atmosphere, ma'am.
Yeah. Mostly it is used in the, particularly in the gas industry and other industry, where they put this to detect the moisture in various. If you do in the particular, if you take the gas chromatography, there are moisture sensors. And they detect the changes in the moisture in the environment. Yeah.
The sensor is used in hospital, ma'am.
Yes, very much. For instance, our thermometer is analog or digital. It's a very good sensor. Like that, every, like our the blood pressure monitor, everything has some kind of sensor material.
Ma'am, types of sensor, ma'am. Types of sensor.
Types of sensor, as ma'am also said, and I also mentioned, like it is based on the quantity that is being measured. For instance, if you want to measure pressure, then it becomes a pressure sensor. If you measure, like if you want to measure, like for construction field, like if you have a like civil engineer people, they use the tilt sensors for to check the leveling and everything. Like that, there is various type of sensors in the applications. Yeah.
Okay, ma'am.
And there was few questions in the chat box.
Any more question? Yes.
Yes, ma'am.
Yes, I will present the question from the chat box. There is a question from one participant. The person has asked why you have chosen diamond. What is the reason for choosing diamond for your work?
Okay. Diamond, like carbon-based material, is one of the interesting like material for making sensors. And but they have graphite and Buckminster fullerenes have been used for a long time, almost like 30 years in research, but they have their own limitations. So people started exploring the diamond. So, but natural diamond or the normal diamond with all carbons does not give the expected properties. Then people started thinking about using the colored diamonds, which is having a different types of, other than carbon, there'll be another element present. So one such idea is to incorporate nitrogen. Not only nitrogen, you can put boron, you can put germanium also, and silicon in that, but their properties are different, and of all the easy to handle for biological system is nitrogen vacancy diamonds.
Yes, there is one more question.
Sure.
That is a CC bond is the strongest bond. So that participant has asked, how is it possible to knock out the carbon atom and replace it by a nitrogen atom? And also, what is the reason for choosing nitrogen atom?
Yeah. I think I answered this question before also. So the carbon bond is the strongest bond, yes, of course. But by doing when you heat it up to 35 electron volt, actually all the bonds get a little disassembled. So in which, and after which you anneal it at 800 degrees centigrade in a very slowly annealing process, not a sudden annealing process where you have to do it at 800 degrees, very slowly annealing process. And then one of the nitrogen carbon will be, and also you have to impinge with nitrogen gas. So some of the carbons will be replaced with the nitrogen. So that's how we incorporate nitrogen instead of carbon, and also the vacancy site. Why do we not only nitrogen? You can people have done with boron, silicon, germanium. Each one of them have a different kind of optical and the spectral spin properties, and optical and the magnetic properties, and this kind of replacement is very makes the system also stronger, and also it gives the desired properties, like we can use it for spectroscopic studies. Yeah.
Yes, there is one more question from the
Sure.
participant.
Sure.
How fluorescence and graphite formation is avoided during the synthesis of diamond?
Okay. This it is all in the laboratory scale. We make use of CVD, that is the carbon vapor deposition method, and in which all the parameters are optimized over like about 10 years. So you make sure that you get like pure, ultra pure diamonds. All the impurities and the fullerene or other types of balls or other allotropes of carbons are avoided. So it has been optimized, yes.
Is one question from Dr. M. Subramanian.
Sure.
Is there any other method to prepare NV diamond?
These are the two methods other than naturally occurring. One is the high pressure, high temperature methods at the industrial scale, and the CVD in the laboratory scale. These two are the methods so far, as of I know. Yeah. Another one is the naturally occurring diamonds. Yes.
Is one more question.
Sure, ma'am.
What type of sensor is used to fabricate, to detect heavy metal ions present in water bodies using thin films?
Well, that you have to have which we have to take a material which can sense metals. Like for instance, if you're detecting lead or chromium in like the heavy metals in the water or other process, then we have to choose a material. Basically, people choose ceramics or zeolites in which the sensor can be made, which can sense the heavy metals. Ma'am, I can't hear you.
Is there is another question, madam. Whether you can suggest another other good sensor metal other than diamond? What is other metal other than diamond, which is used as a sensor?
Yeah. As I mentioned during the talk, diamond we chose because of its electrical and spin properties, what we need for our studies. But you can always choose other. Graphite is a good sensor. Full Buckminster full income, considering the carbon allotropes. Other than that, there are a lot of metal oxides. Um, Ceramics, zeolites, different types of nanomaterials like gold, silver, hybrids. Everything can be used as a sensor material. Yes.
Another question from another participant.
Sure.
That is usually purity is a reflection of sensitivity. So how far is NV sensor sensitive?
It's it's very pure and it's very stable. By doing imaging, we can see how much we incorporate. So like I said, like this build is about 10 to 15 years old. So over the period, it's been optimized, so we can actually make single NV centered diamonds, also multi-centered NV diamonds. So we take the chip, the diamond chip, and then when you do the imaging, you can actually characterize the NV centers, and it's very pure, ultra pure. Yes.
Yes, sir. That's all, madam. Thank you.
Okay.
Now, with a deep sense of gratitude, I would like to thank Dr. SriRanjini Arumugam for sharing her work, experience, and knowledge about diamonds, nano diamonds, and nitrogen vacancy in diamond as a sensor and its various applications. Thank you, madam, for spending your valuable time with us. I also thank Dr. SriRanjini Arumugam for her patience in answering the questions. On behalf of the participants, I extend our thanks to you. Thank you, madam. I
Thank you.
also thank the participants for patient listening and active participation. Thank you, one and all. Now we will have the photo session. I think all the participants can keep your video on for the photo. Kindly keep your video on. Mr. Dinesh, can you please take a photo? Mr. Dinesh? Participants, kindly keep your video on. Yes, thank you, participants. Thank you, madam. Tomorrow we will have two sessions. Yes, tomorrow we will have two sessions. The first session will be at 2 p.m. So kindly join just 10 minutes before the session. We expect all the participants to attend all the three sessions to receive the participation certificate. Yes. Let us meet tomorrow. Thank you.